And today what we're going to do is using the CNN model to do the classifications, right? Because our input will be imaging, right? So here is a quick review. If you remember, last time we talked about the input dimension and output dimension after you use the convolutional kernel, right? Within a convolutional kernel, you can choose to padding, which means that you add additional columns, right? Next to the horizontal row and the vertical columns to make sure that when you use the kernel filter, you can keep the dimensions and scan over it to keep those informations at a corner. So that's the meaning for using the padding. And the stride says that if you want to scan your overall images, how many information you want to skip, right? So generally you use stride 1 or 2, okay? And here is the formula. Suppose we have an input size and input, and because this is a square matrix, meaning that for your images, generally the input is 256 by 256 by 3 channels, RGB channels, or 128 by 128 by 3. That's a typical size of the images. Then your input dimensions plus 2 padding, because each side you have 1 padding, so plus 2 paddings minus k. So k is the size of your kernel. And then divided by the stride size so that you can estimate the number of the output dimension. And don't forget to plus 1. So this will be the output dimension. If we look at an example, now let's start from the input. Suppose you have a 32 by 32 by 3 images, the input size. So which is something like this. So 3 different channel RGB, and the size is 32 by 32. That will be input. Now let's use, suppose we use 1 by 1 by 12 filters, kernel filter. So K, the size of kernel, let's say is 1 by 1. Which means that you will use this kernel to scan all these 32 pixels. All of them, 32 by 32, you'll scan all of them. And not just for the first channel, also all the rest of the channel, you'll scan them and combine it together. Right? Okay, so that's just one case. Maybe it's just one of the kernel we use. And we can use multiple. So maybe we can use, follow the example, we can use 12 kernel. So every of them will do the same thing, scale all the RGB channels and combine them together. Okay? Great, so let's check. Let's assume that we have a kernel 1 and maybe no padding, so P is 0 and stride, just use 1. So based on our equations, the n output will becomes 32 plus 2 times 0 minus 1 divided by 1, and then plus 1. So again, it's still 32. Okay? Great. And then we have 12 kernels. So you can imagine that now your new output, again, it's 32 by 32, but you will have, so on and so forth, you will have 12 channels after the kernel. Okay? Any questions? So the previous layer is input 32 by 32 by 3. Now after the convolutional kernel is 32 by 32 by 12 because we use 1 by 1 kernels and we have 12 kernels. Okay? Great. And after that we use value. And as I mentioned, value or hyperbolic tangent or sigmoid, they are all just activation functions. So we don't need to worry about the dimension. It's not going to change, but the number within it will be different after the activation function. So the size is still the same, 32 by 32 by 12. And now we can work on the pooling, called the pooling layer. So imagine that after the kernel, right? The previous example, the kernel give you a 4 by 4 output. Original dimension is 6 by 6. Now kind of reduced to 4 by 4 after your kernel. Then continuously we want to reduce the dimension to get the most important features. So we use so-called pooling layers. So the pooling layer is like this example. So now this is the output, right? 4 by 4, we have just seen that. And then we use a 2 by 2 pooling. Here, 2 by 2, the same skills. You put these pooling layers on your original output from the convolutional kernel, right? So look at this for 1, 1, 5, 6, right? And then we use the maximum pooling to only find out the maximum value among these 4 pixels, so which is 6, right? So it means that we capture our 6 here. Again, we take a look at the other 2 by 2 matrix here, right? And what is the maximum number here? 8. So we only output 8 here. So similarly for this one, we only output 3, and this one, again, we only output 4. So this will be the final output after your pooling layer. And inside the pooling layer, you only capture the most important pixel or value or the informations from your previous layer. Okay? You get that? Right. So maybe we can look at this again. So it means that when we use a pooling layer size, which is equal to 2, right? 2 by 2. And then we use stride also 2, which means that next time when we move on to the right, we skip 2 columns. So first time you only look at this and find out the maximum one. So this one is the max. And the next time, so this is column 1, 2, 3, 4, right? So we skip 2 from 1 to 3, and then we find another maximum one, which is this one. Similarly here, we find the maximum one, which is this one. And last but not least, this one is the max. So your output becomes max, it's a max 1, 2, 3, 4. Right. This will be your output. And you can imagine that in previous case, right? If you look back to the images such as maybe this one. Yeah, this one. This one is better. So when you use the maximum pooling, right? And you look at this grayscale images, you realize that all this, if you 0, for example, is there like a background, like a white background. So there's no information within that pixel, right? But if you keep the maximum one, the pixel number which has the maximum value, supposed to be maybe 256. So that will give you the most clear and significant informations, right? So that's why they use the pooling layers to reduce the size, but in the same time to capture the most important information. Okay? Great. So that's the output of pooling. So the size is still the same, 32 by 32 by 12. And now we can work on the pooling. because we think 32 is too large, so it gives you computational burden. So why not just use a pooling layer to reduce the size? So we use 2, the size of the pooling 2, right? Just as our previous example, and the stride also equal to 2. So we use the pooling with the size, I use F equal to 2, and S, which is stride, also equal to 2. So the size is 32 minus 2 divided by 2 plus 1. It will be 16. So it means that they will become 16 by 16, and again you have 12 channels. Okay? So it becomes 16 by 16 by 12. Remember, this is just one image. In reality, when you work on the image set as your training data, you have a lot of images, which is so-called a batch size. So every time doing your training iteration, how many images are you going to feed to your CNN model? That's so-called batch size. So suppose you have maybe 100 images as a batch size. So every layers after this kernel pooling, you're supposed to get maybe 100 by 16 by 16 by 12. So it's a 4-dimensional tensor. So you have a lot of parameters within it. So that's why I say nowadays you need to use the TPU or GPU, to efficient the overall calculations. Okay? Now, after that, we can work on the fully connected layers. So 16 by 16 by 12. Let's do the flatten. Let me just here. So what will be the size here? 16 by 16 by 12. It will be 3072. So the dimension for this array will be 3072 by 1 after flattening. Then the number of the fully connected layers depends on you. So here is actually hyperparameters that you also need to play with when you work on the real world case. So maybe let's say from original 372, we reduce to 512, and then maybe 128, and eventually we make the classifications. So here the example I'm showing you is 10 by 1. So what is the 10 by 1 means? It means that we need to classify the final category into 10 different cases. So in this example, which I'm going to show you specifically, the 10 categories represent the 10 digits. 0, 1, 2, 3, 4, so on and so forth to 9, which is the 10 digits. So this one is a classic image set. It's so-called a handwriting digit data set. So you see that what I'm going to show you later, the images, is describing the handwriting digit number. So you have 10 different outputs, right? 0, 1, 2, so on and so forth to 9. So every images you input in the CNN is a handwriting digit. And then the output of the CNN is trying to classify which digit that image is. Okay? So that's why you have the final output 10 by 1.